Okay, so welcome to the 19th video in the Discrete Structures series, and we're going to start this video with a look into computer arithmetic with large integers. And this is one of the most important applications of modular arithmetic and the Chinese Remainder Theorem. And under the topic of matrices, we're going to cover 0, 1 matrices, and these are also called Boolean matrices. And we'll look into the different matrix operations, and they are join, meet, and Boolean product. And with these topics, we will have completed our second chapter of integers and matrices. And from the next video, we'll be looking into logic and proof methods. So let's get on to the topics here. And I want to begin with the computer arithmetic with large integers. So I want to start this by first showing you an example with a small number so that we can see what's going on. And we will also demonstrate an example with larger numbers so that it is clear how things work on a larger scale. So let me start my example by doing something seemingly random. So I want to start with two numbers, let's say 2 and 3. And I could take more than two numbers, but the only requirement is that I want the numbers to be pairwise relatively prime. Okay, and we have covered the idea in our previous video, but just to recall, co-prime numbers are simply numbers that do not share a factor. 2 and 3 are not very good examples because they are already prime. But if we consider the numbers 9 and 16, you can see both these numbers are not prime. But if I look into their factors, 16 is just 2 raised to the power 4 and 9 is just 3 squared. So you can see the factors of 16 contains only 2's while the factors of 9 contains only 3's. So there is no common factors. Therefore 9 and 16 are co-prime. Okay, so 9 and 16 would also have worked in my choice here. But I'm choosing 2 and 3 because that results into smaller numbers and makes it easier for me to demonstrate. And as I said, we'll look into numbers with bigger examples shortly. But hold on with me. So what I want to do here is to find representations for all numbers that are below 6. And the reason why the limit is 6 is because the product of 2 and 3 is 6. So I want to find the representation for 0, 1, 2, 3, 4, 5. Okay. And I want to write pairs here. So I simply want to write whatever the remainder is for this number modulo this number. So what is the remainder? When I divide 0 by 2, the remainder is simply 0. And similarly, when I divide 0 by 3, the remainder is also 0. So let me continue on this fashion. For 1, both of these will still leave a remainder of 1. So I just have 1, 1 here. And now let me do the other ones. Okay, so I've written the corresponding pairs for all these numbers. And you might be wondering what is the point of doing all this. And I'll show you the purpose shortly, but first let's make a couple of observations here. The first observation I can make is all of these pairs are unique. You will not find two pairs that have exactly the same elements. And another interesting fact, since my biggest modulus is 3, there can never be a number more than 2 in any of these pairs. Okay, so what we have been able to do here is to represent these numbers 0 through 5 only using the numbers 0, 1 and 2. But obviously the next question is, why did we even choose to represent these numbers this way? Does it help at all? And it turns out that it helps a lot. So for example, if I took any two pairs and added them, the resulting pair would also represent the number, which is the corresponding sum of those numbers added together. So what do I mean by that? So let's consider 3 and 1. I can see that the pair representation for 3 is 1, 0 and that for 1 is 1, 1. Okay, and if I add these pairs, let me do the addition and write the result here. So I just want to do the addition component wise. Okay, so the first number will be added to this one and the second number will be added to the second number here. And obviously because I'm working with this moduli, I'll need to reduce my results modulo these numbers. So with that in mind, let's try to add 3 and 1. And I can see that the first number in these pairs, 1 plus 1 is equal to 2. But I want to reduce that 2 modulo 2. So 2 divided by 2 leaves a remainder of 0 and that's what I'm writing here. And now let me add the second numbers. If I were to add 1 plus 0, that would result to a 1. And 1 more 3 is already 1. Okay, it doesn't get reduced anymore. And if you try to find this number in this list, that is the correct representation for 4. So we have demonstrated something really powerful here. If you start with any set of numbers that are co-prime, you are able to represent all numbers from 0 to the product of those numbers. And how many co-prime numbers you initially chose will determine how many numbers will go into these representations. And once you have this representation, you can perform addition like we demonstrated here. And I want you to verify for yourself that subtraction also works similarly. Okay, I could just subtract the numbers component wise and take the respective moduli and the result would also be correct. But what I cannot do is consider operations that produce a result outside of my range. So if I were to try to add 4 and 3, the result is actually 7. But I cannot get a 7 because 7 is not within my representation. The answer that I'm going to get is going to be 7 modulo 6 in that case. Okay, and once addition works, multiplication should follow automatically. Because if I'm multiplying A with B, I'm just adding A with itself B times. So that means I can directly multiply the values in this representation and the resulting representation would also be a correct result. For example, consider 2 times 2, multiply this with itself. You see 0 times 0 is 0, matches with the 4, and 2 times 2 is 4 and 4 mod 3 is 1. So that also matches with the 4. So I could perform multiplication and also get the right result. And in case you are wondering about division, division cannot be performed in the normal sense. So please do not divide these numbers, you will not get the right result. What you actually need to do is to multiply one number with the modular multiplicative inverse of another number. So let's say if I need to divide a pair AB by CD, and of course these are pairs, then I find the modulo multiplicative inverse of C mod 2, and then I find the inverse of D mod 3, and that will give me a new pair, and then I multiply that pair with AB, and that will be the result of division. So division is a little bit different. It follows the modular multiplicative inverse, but that is out of scope of our discussion and our syllabus anyway, so we'll just leave it here. So in this example, we just chose 2 and 3, and that did not help much because these numbers were small. But I want to show you an example. Let's consider the moduli 99, 98, 97 and 95. Okay. And I want you to verify that all of these numbers are co-prime. So none of these numbers share any factors. Okay. And this time my notation would use quadruplets. And let me show you an example. 33, 8, 9 and 89. So this quadruplet is a unique representation of the number 1, 2, 3, 6, 8, 4. And I have another example in my note. Let me put that here. It's 32, 92, 42 and 16. And this is the representation of 4, 1, 3, 4, 5, 6. You see, and if I want to add these numbers, I only ever have to add numbers that are less than 99. And let's say I have a slow performing computer or an architecture which can only work with numbers less than 100. And thanks to this representation, it would be able to work with those numbers. It would be able to make this addition. And in fact, it would be able to work with any numbers within this range. Okay, so this is a very big number. And all I need to do is to ensure that my results are smaller than this number. Whatever operation I'm taking, whether it be addition, subtraction or multiplication, I want my results to be within this range of this number. So let me demonstrate this addition for you. So this gives me 65. I can just add. This is 100. I have 51 here and 105. Okay, and there is one reduction to do. I want these numbers to be within my moduli. So let's ensure that 65 is already within the moduli. 100 is 2 above 98, right? So I would get a 2 here. 51 remains the same and 105 gets reduced to 10. Okay, and if I were to add these numbers normally, I have my sum noted here. I'll write it down, 537140, and this is the representation for this. And to make sure that you are not lost, it means that this is the only number that leaves a remainder of 65 when divided by 99, leaves a remainder of 2 when divided by 98, a remainder of 51 divided by 97, and a remainder of 10 when divided by 95. And if that sounds familiar to you, that concept comes from the Chinese Remainder Theorem. And let's see why that is useful. We have established that this representation of numbers allows us to work with much smaller numbers to achieve the same result. But how do we actually go back from this representation to this representation? What if these calculations were happening on a computer? So as long as it is doing calculations internally, it is fine. It could just work with these representations. But in the case where you actually need to convert these quadruples into the numeric representation, we need to go back to the Chinese Remainder Theorem. Okay, so let me demonstrate the point here. And our goal is to be able to find this representation for this number. How are we going to do that? So like we talked about just a minute ago, I want a number x which leaves a remainder of 65 when divided by 99. Similarly, the same x needs to leave a remainder of 2 when divided by 98. And that comes from the fact that this 2 corresponds to this modulus here. And the same number should leave a remainder of 51 when divided by 97. And the same thing should be true for 10 mod 95. Okay, and we have already looked into how we can solve these kind of linear congruences in our last video. And that involved the Chinese Remainder Theorem. As long as these numbers were co-prime, and in this case they are, we are able to use the Chinese Remainder Theorem in order to resolve this. So I invite you guys to try this out and see if you can reach this number. Okay, we'll move into the next topic of our video, and that is 0, 1 matrices. So I think this should be a straightforward discussion. A 0, 1 matrix is simply a matrix where each element is either a 0 or a 1. Okay, so this is a typical example of a 0, 1 matrix. And these are very similar to normal matrices, except the operations kind of change a little bit. So for example, the operation of multiplication gets changed into the AND operation. Okay, and the addition operation gets converted into an OR operation. And just a matter of terminology, OR is also called a join and AND is also called a meet. And you should be able to recall from Boolean algebra in your digital logic course. So whenever I'm performing an AND operation, the result is 1 only if all the bits are 1. Otherwise AND will be 0. And in case of OR, well, any one value could be 1 and the result would be a 1. So both could be 1 or any one could be 1 and the result would still be a 1. But I think a better way to tell the same thing is an OR is 0 only if both things are 0. Okay, otherwise it is a 1. So in case of AND, both 1 will result to a 1 and other cases it will be 0. And in OR it's just the opposite. Both zeros will be a 0, in all the other cases it will just be a 1. So in terms of this join and meet, we define the Boolean product of matrices and the rules of matrix multiplication are exactly the same. Okay, so if the first matrix has R1 rows and C1 columns and the second matrix has R2 rows and C2 columns, the size of the resulting matrix would be this one. Okay, so it always works that way. So the row in one matrix is going to be equal to the columns in another matrix, and whatever the unequal numbers are going to determine the dimension of the resulting matrix. So if I multiply a 2 by 3 matrix with a 3 by 4 matrix, the result is going to be a 2 by 4 matrix. Okay, because 3 is the common thing here. Okay, so that is all the theory we need. Let's look at a couple of examples. Okay, it's given to me that A is this matrix and B is this one. And I can see number of rows here 3, number of columns here 3, right? So these matrices are compatible for multiplication and their product is denoted this way. This is for Boolean product of matrices. Okay, and let me follow along this process. So I take this row and this column to begin with, and instead of multiplying I need to take an AND operation. So it will be 1 and 1 or 0 and 0. So let me write that down, 1 and 1 or 0 and 0. Okay, so this is going to be my top left term. And let me resolve just this one so that you guys have an idea. 1 and 1 is 1, 0 and 0 is 0. Okay, and when I'm taking an OR operation, this will give me a 1. So let me directly write the result here. It is going to be 1, 1, 0, 0, 1, 1, 1, 1, 0. So I calculated this one from here, but you could follow with all the similar terms and it will give you 9 terms. And you could see that, right? This is 3 by 2, this is 2 by 3, and this is common. So my result would be 3 by 3. And there's one more question that I want to draw your attention at. So A is given to be this matrix. And the question says find A to the power n. And by the way, this is the notation when we use when we want to say multiply the matrix A with itself n times. And it says find this for all n greater than 0. Okay, so whenever you see a question like this, you should start with calculating A square, A cube, A4 and higher powers. But you should expect that at some point the matrix will converge. Okay, so no matter how many powers you take after that, it will just be the same matrix. So please try this out as well. And I'll tell you what the intermediate results are going to be for you. So you first calculate A squared, multiply A with itself. And I hope this is clear. This is just multiplied with itself. Okay, and that will result into a 3 by 3 matrix. Follow the exact procedure as you did here. And then you should get this value. Okay, once you have A squared, you multiply that with A again, and that should give you A cube. That is going to be this value. And to get A to the power 4, you multiply A square with itself, or you could multiply A cube with A. Both of them will give you A to the power 4. And then in order to reach to 5, you multiply 3 with 2. Okay, and then you'll find that the fifth power is an identity matrix. So whenever you reach A to the power 5, you should find that it is a matrix containing only ones. And once this happens, multiplying this more would only result to the same matrix. And therefore your solution would list the powers of A until 4. And then conclude that all higher powers of A from 5 is the same matrix, the identity matrix in our case. Okay, so that is the discussion for this video. And this discussion also completes the second chapter of integers and matrices. From the next video, we'll be starting the chapter for logic and proof methods. So I'll see you guys in the next video. Until then, have a great day and bye.